Hi guys, BuildZoid here, and today we're going to be talking about this right here. Now, unfortunately, I can't really figure out how to do a good video about this, so we're just going to do it this way. Anyway, so yeah, I basically got the idea to put liquid metal on a 3950X for the simple reason that a 3950X can pull a ton of power, and it has a relatively small IHS. Like, the IHS is just not that big, and you can make this chip pull easily in excess of 200 watts. Liquid metal, excels in any scenario where you need to move a lot of heat across a small cross-section, right? Which is why it's so popular in, like, delidding and that kind of thing, is like, the reason you use liquid metal on delidded CPUs is because CPU dies are freaking tiny. So if you can get, the useful cross-section you have for transferring heat from the die to the IHS is very small, so you want the cross-section that you're using to have as low thermal resistance as possible to compensate for the fact that it's not very large. And as a result, liquid metal in under IHS applications just decimates thermal paste. Like, it's not even a contest. It's like thermal paste under an IHS, just like, it's not okay. As far as I'm concerned, there are plenty of places where thermal paste is fine, but under an IHS, is not one of them. But 3950Xs are soldered, and direct die on Ryzen is annoying because of the way the socket is designed. Like, this part of the mechanism is actually generally taller than, I think, the CPU, the actual dies of the chips. So because of that, trying to direct die a 39 or delid a 3950X, not really something you want to do, but that doesn't stop us from throwing liquid metal on top of the IHS because, okay, so maybe the heat gets from the cores to the IHS pretty quick, but how quickly can we get it from the IHS to the AIO? So for the test setup, I ran 4.2 gigahertz, which might sound like a pretty low clock speed. That's because I'm actually using a very heavy workload. And it's also static so that we don't have PBO, screwing with the test results. At 1.3 volts, mode 5 LLC on the MSI X570 Godlike. Mode 5 LLC is rather droopy. So there's a lot of droop on that. So we're not actually doing 1.3 volts under load. LLC. MSI X570 Godlike. So thank you, MSI, for the motherboard, by the way. It's a pretty good board. It's just way too expensive. Actually, it's a great board. It's just way too damn expensive. It's so freaking expensive. It just costs too much as far as I'm concerned. Anyway, 4.2 gigahertz, 1.3 volts, mode 5 LLC. The workload was Prime 95. Of course it was, because, look, if you're going to be testing any kind of cooling thing, you want to test at the highest possible heat loads because that blows up the differences. So Prime 95, 128 KFFT size, which is insanely hot. How hot? Well, this was drooping down to 1.187 volts on the SVI2 TFN sensor. And it was pulling 244 watts. About 244 watts. So, yes, very, very hot, very power hungry. Perfect application for liquid metal. So for the cooling system, I was using an EVGA, and then somebody was like, will he finally tell us the results? We're getting there. You need to know the test setup. Like, this is important. If somebody wants to prove me wrong, I want them to be able to do it properly. EVGA 280 millimeter, 280 CLC, I think is the actual product name. Actually, it's CLC 280. I don't care. Plus Corsair maglevs. I'm using Corsair maglevs on it. 140 millimeter, everything is maxed out. All RPM, like pump RPM on the CLC is maxed out. Fans are maxed out. Everything's maxed. All max RPM. Because the thing is, we don't want, like, the rate of flow of the water to limit our thermal transfer. We don't want the fans to, like... We're testing the thermal paste here, right? So, anyway, that's the test setup. Oh, and also I had 2x8 Corsair Dominator RGB 3600 CL16 memory. 2x8, 3600, 16, 18, 38. Right? Because the TRP and TRCD are the same thing. So that's the memory configuration. So then, water. Oh, and also 1.15 volts SOC. There. That's the one thing I forgot to mention. 1.15 volts on the SOC. Anyway, so let's talk about the results. I was monitoring the water temperature, not ambient temperature. So first we go. Actually, I'm just going to write out what it is. So I used NTH1 for the thermal paste representative. NTH1 is a pretty damn good thermal paste. I don't have any Cryonaut left. Corsair's TM30 is not a good thermal, is not like good enough for this. And the KPX, I didn't feel like using KPX. So I just used some NTH1. And then of course I used, for the liquid metal, I used Conductonaut, from Thermal Grizzly. So not there. So I was monitoring the water temp with a thermocouple just glued to the radiator. Actually, it's not glued. It's like blue tacked onto the radiator. And CPU temp. And the reason why I'm monitoring water temp and not air temperature is because the water determines, like, that's the water, like the water temperature is more stable than air temperature. It's easier to measure than air temperature. And what else is there? Like, that's ultimately the thing that affects the cooling of the CPU, right? Because that's the water going into the water block. So I was actually monitoring the temperature of the water coming from the return from the radiator to the water block, not the water block to radiator connection. Because water block to radiator is the hot water side. Radiator to water block is the cool to down water. Anyway, so that's our water temp. And water temperature for the NTH1, which I ran first, was 28 degrees Celsius. And it achieved a CPU temperature of 88 degrees, roughly. There's like plus minus 1 degree on everything here. Mostly because, like, I set out to do this testing with, like, this is going to make such a massive difference that 1 degree of error doesn't matter, or the result is useless. Right? Basically, I was looking for a temperature drop that was actually significant. Because if it was like 2 degrees of a temperature improvement, then it's not worth it just because of all of the issues that liquid metal has when, just because of what a hassle liquid metal is, in my opinion at least. Like, and I did used to daily liquid metal. Like, there was a time I dailied liquid metal. And since then, I've basically not, since then I've only used it in like delid applicate, like direct to the die of CPUs. Because I used it on GPUs. We're going to cover the issues I ran into later. Nobody probably cares. You want to know the results. For the Conductonaut, which I ran second, which is why the water temperature ended up higher because the room warmed up. You know, there was probably some residual heat sitting in the water after the first run as well, because I just swapped systems, right? So this is why I'm monitoring the water temperature and not the air temperature, because I don't have to wait for the water temperature to like stabilize or anything. I can just go like, well, the water temperature going into the water block right now is 28.5 degrees, and the CPU is running at 80 degrees, which is a big enough temperature drop to go, yes, this is a big enough difference that, you know, you may as well consider it. Because actually, like, the fact that this is 0.5, which also that thermometer, well, plus minus 1 degree. So anyway, so I'll just call that like an 8 degree drop. And that, in my book, is almost like, I'd say that's pretty much worth it. Especially if it were like, if you were testing with an even better cooling system, right? Because here's the thing, if I ran a higher voltage, like look, the 3950X is very expensive, and thanks to my patrons, I was able to buy it. I have zero intention to run that chip into the ground, unlike the 3700X, which seems to have already, which I seemingly have already managed to degrade. Good job me. So, unlike with the 3700X, I am babying the 3950X for as long as I have it until it's like for next 2 years, I'll probably not do anything too stupid with it, just because it's way too expensive. Like, I'm not killing a 3950X. Same as I'm not killing my 7940X. It's just like, nope, costs too much. Definitely, so I don't really want to be running my 3950X at over 90 degrees at over like 1.2 whatever volts, right? So because of that, if I had a better cooling system, we could test at an even higher heat load, right? Like we could test maybe at 300 watts, and that would make a bigger gap between these two. And actually, you could probably calculate how much of a gap. Well, I'm going to throw out an estimate. Somebody who knows more about thermal physics than me might end up correcting me in the comments. But if we go from 240, and so this is doing like a 60-degree delta, right? And actually, we're just going to round that down. So that's going to be 240 over 60. So that's what is that? That's like 4 watts per degree. And this right here is like, okay, what's that delta? That's, damn it. Okay, wait, no, we're not going to do this the lazy way. Because you could, theoretically, from these results, you can calculate what you'll get at higher wattages. And I'm actually pretty sure I'm doing this correctly now. So we're actually going to do it properly. So we're going to do 244 over 60. Yeah, so that's 4.06. Just going to pull that off screen for a bit. And everybody's like, Buildzoid, your videos suck. It sucks to be you, doesn't it? Go find somebody else who does this kind of testing. Then you can complain. I love how I have no competition. What else? So 80, I'm just not even going to try to do that in my head because I'm going to screw that up. Yeah, so that's 51. That's a big difference. Okay, so 244 divided by 51.5. 4.73. That's actually, that's significant. So that's 4.73 watts per degree. Damn it, I did it backwards. I wanted degrees per watt, and I did watts per degree. I'm dumb. Yeah, I did it backwards. Well, screw it. Okay, wait. We're gonna do it the right way around. So it's 2, 4. Actually, I don't know why I bothered to calculate the other one. Like that one doesn't matter. Anyway, so it's 51.5 divided by 244. Yay! And now we can multiply this by 300, and we get 63 degrees. So what that tells us is that with the liquid metal, at again, like this is not including the fact, like assuming same water temperature, right? So 300 watts at and the same water flow rate, which, like, if we actually ran 300 watts into the 3950X with the EVGA 280 CLC, even with the fan swap, it was like that would not be okay. It would get way too hot. But like, because the thing is, we wouldn't be like water temperature would go up, and then you, on top of that, you have the increase in heat output from just the temperature delta from the CPU to the water, and then you have the increase in the water to air temperature, and it's just like, yeah, no, like it's going to overheat. So, like, well, it's not going to overheat, but it's going to run so hot that I'm not going to be comfortable doing it. So 300 watts at 28.5 degrees water temperature would give us. So we're just going to add 28.5 to the result. Would give us 91 degrees. Okay, so yeah, like it would still not be very okay to run 300 watts, even with the conductanol. Like if you had a better water block that had better thermal transfer, and that would further improve the water to CPU delta, right? So better water block, more cooling, like colder water, right? That kind of thing. So you could actually push this to the point where you could run with enough adjustments to the cooling setup, I'm pretty sure you could run a little over 300 watts at under 85 degrees with liquid metal. Without liquid metal, you probably wouldn't be able to because, well, actually, let's do the water for comparison. I mean, the regular NTH1 for comparison, right? We can go 244, actually no, 60 divided by 244. We end up with that. We multiply that by 300. Yeah, you'd get a 73 degrees So actually, it would go to, so, you'd have a 73-degree delta, which at 300 watts, at 28.5 degrees would give us, no, I am not testing that. 102 about 102 degrees. So yeah, and this is my point, right? Like theoretically, that gap is going to widen the more heat you run into the CPU. So the advantage of the liquid metal becomes bigger and bigger the higher heat you run. If we were testing at like half as much wattage, instead of 300 watts, if we were testing at like 100 watts, the difference in temperature between the two thermal pastes would be much, much less. So at stock, it doesn't make sense to run the Conductonaut. But if you're absolutely wailing away at the CPU with something like Prime 95 at rather low voltages, because 7 nanometer just runs really, really hot, yeah, the Conductonaut makes a ton of sense. And if you want to go even faster, then the Conductonaut makes more sense. So yeah, anyway, other complaints I have for this testing. So there's my results, right? There's some fun thermal calculations. Wait a minute. I actually do find these fun. Like, I love this kind of thing. So, I guess any of some, like, well, any hope of me acting like, well, okay, no, I can't even English anymore. Too excited by data. I need to chill the hell out. It's not that exciting. It's just thermal paste build Zoid chill. Anyway, there we go. So this is one of my main complaints for my for the testing. So this is with the thermal paste, and this led to some very, very annoying adventures with the liquid. This video is going to end up being way too long. Well, welcome to AHOC. BuildZoid gets excited about calculating some random gibberish that nobody actually cares about, and the video ends up 40 minutes long. Ends up 10 minutes longer for it. Anyway, yeah. So this right here. So a lot of people might be like, this bald spot in the middle is a problem. No, that's fine. That's good. If this was an Intel CPU, that's great, because that bald spot is where the pressure between the water block and the, well, it's not a water block, between the AIO, which has a cold plate. Okay. So between the cold plate and the IHS is the highest. Right? So where the pressure is the highest, that's where it squeezes out all the thermal paste, and that's how we get this bald spot right in the middle, which is, okay, that's good. On an Intel CPU where your die is located right around there and roughly that size, that's great. On an AMD CPU where your IO die lives, where I assume the IO die is located over here, and the CCDs are, sort of up in this area, this right here is not good. So I think potentially the test results I have for the thermal paste, like the thermal paste might be suffering to the fact that the AIO is not very flat. At the same time, the liquid metal was definitely suffering to the AIO not being very flat, because I ended up reapplying liquid metal 4 times, I think, before I finally got like good temperature results. And the reasoning for this is very simple. So we have our CPU, which is relatively flat, and we have our CCD, actually, we have our CCDs like here, and then we have our, actually, I'm making it way too wide there. So we have our CCDs over here, we have our IO die over here, right? So we have CI for IO die, then we have our, then there's the solder between the two, and there's our IHS, and we're just going to pretend that the IHS is flat. I don't think it is. I've never seen a CPU come with a stock, like a flat IHS at stock. But I've not lapped my CPU because, again, I've been babying it, though I do plan to lap it eventually, especially now that there's liquid metal on top of it. Like, I'm going to be lapping it. Liquid metal ruins inscriptions on IHSs relatively quickly. And I actually want to keep running liquid metal on the chip. So, because it's freaking, like, it's 8 degrees, man. Like, 8 freaking degrees. Like, that is actually significant. At least to an overclocker like me. To most people day to day, I get it. You don't care, especially if you're running like PBO. You don't care, but I care, and 8 degrees is good enough for me. If I had a better cooling system, then, we could probably get away with more. But for convenience, I was just testing with an AIO instead of like a proper full custom loop. with like a better water block, higher water flow rate, bigger radiator. Like we can get the water temperature lower. We can also make because the thing that really sort of, like one of the advantages that you get with a custom loop is that the water flows through the water block much faster, which means that the period of time that basically the water is cooler while in the water block. So you don't have hot water sitting in the fins of the water, in the micro fins. You have fresh water in the micro fins much faster than in an AIO, because AIOs run pretty anemic pumps. So anyway, but I don't know how much of a difference that would make. Like, I don't. Here's the thing. As much as I find a lot of thermal stuff very interesting, I find the testing for it to be extremely tedious. And as such, I don't actually do, I don't do water block reviews. I don't do heatsink reviews. I don't do any of that because it's tedious. It's very interesting, and I love the data. And, it's very hard to find anybody doing, the testing properly, in my opinion. But it's freaking tedious, so I'm not doing it myself. Well, maybe so, yeah, that's my, I love cooling systems, but I'm not going to test them myself anytime soon, or at least not more so than something like this, where it's just like this is such a big difference that it's cool. I'm not going to go out and set up a system where you have a margin of error where it's you don't need an 8-degree drop to see oh yeah, this is actually significant. Anyway, where was I? So we have this lovely diagram here, and then we have our very not flat water block, right? Which basically looks like, yeah, we're just going to draw a circle. There, that's our water block. So the thermal paste, right? Because when I apply thermal paste, I just throw on an X. The reason why I throw on an X instead of what a lot of people recommend, which is a dot, is if you get the dot size wrong, if you apply a too small dot, then you're going to end up with a tiny little, the coverage of the IHS is going to be awful, and your thermal transfer is going to be equally awful because you're not using the full surface area of the IHS to actually transfer heat. You're just transferring heat through a small patch in the middle, which on a Ryzen, not going to work very well because the cores are off center. So you really don't you want to cover, you want to use every square millimeter of IHS that is available. You want to use it for thermal transfer. So you want thermal paste absolutely everywhere. So this right here with the corners is not great in my opinion, but yeah, well, curved AIO. Man, when I'm not trying to draw a curve, the curve comes out way better. Okay. So anyway, so with the thermal paste, the thermal paste just kind of squeezes out and you get everything filled out nicely. Though it's still not ideal because obviously thermal paste has a relatively low, relatively high thermal resistance. So a thick layer of thermal paste is actually worse for your a thick layer of liquid metal is not as bad for liquid metal performance as it is for thermal paste, because liquid metal is 6 times more thermally conductive generally, right? A high-end thermal paste will be somewhere around 10 watts per meter Kelvin. Most liquid metal most liquid metal alloys are around 60 watts per meter Kelvin, which is 6 times as much. There are thermal pastes that are 15 watts per meter Kelvin, but still, you get the point. Liquid metal is in a league of its own when it comes to thermal conductivity, because it's metal instead of just metal shavings shoved into some silicone oil, which is what most thermal pastes are. Anyway, so the thermal paste, the fact that the block is not very flat, probably not doing the Noctua NTH1 any favors, might be responsible for a lot of the issues. Now, the reason why I had to reapply liquid metal 4 times is because the first time when I apply liquid metal, the problem with liquid metal is if you spill liquid metal on something, it's not like when you spill water on electronics, okay? If you spill water on something and it doesn't immediately up and die on you, then you can just turn off the power, let it dry, and you're probably going to be fine. Liquid metal does not dry when you turn off the power. It never dries. So if you spill liquid metal on something, it also eats solder. So if you spill liquid metal on something, you're in for a very bad day. So because of that, when applying liquid metal, I always go with, I paint it on, and I paint it on as a very thin layer. So I'm pretty sure what was happening in my initial test was I had a a liquid metal application that looked like this. Funnily enough, even with a liquid metal application that probably looked like this, obviously I couldn't actually like look under the water block while it was installed to see if that's what it's doing. But when I pulled like it, I did notice that most of the disturbance in terms of like the how I painted it on, like the liquid metal was only really disturbed right down the center. So from that I did use that, yeah, it was probably something like this, where it's just like, well, there's no contact, like there's just zero thermal transfer over here because air is an insulator. Well, technically everything's kind of like, well, a vacuum is a better, well, you get the idea. Air is an insulator, we'll just leave it at that. An air over here is also an insulator. So this is no good because we want our CCDs to be cool. Now, one of the things I tried was like intentionally loosening the mounting hardware on this side to try get the block to lean this way. Didn't really work. That didn't help at all. So, which I think the main issue is the mounting hardware is like, you know, it's the it's the standard Asetek mounting hardware, so you can't actually like push down more. You can only loosen it because it just stops. Like the thread just, it doesn't have a thread that just continues on forever. It just stops at some point. So because of that didn't work. So trying to get the block to lean onto the CCDs more didn't work. But I just kept reapplying the liquid metal, by which I mean I took the water block off and I threw on more liquid metal. And so eventually I probably got enough liquid metal on there that it built up to like this point, and now it worked properly. But I still think there is room for improvement. If I had a water block that's, you know, actually freaking flat, then we could get away with the really thin painted on layer of liquid metal instead of having to keep adding more and more until it finally fills out the fact that the block just ain't flat. So yeah, with a flatter block, this could probably improve. The thermal paste might also improve. So if I was like doing this to the limits, I would probably lap the CPU, lap a water. Well, I'm not sure if anybody sells a flat water block because it's normal for most water block manufacturers to bow their water blocks because as far as I know, Intel CPUs are intentionally this, like the IHS of an Intel CPU is this. I'm not sure about Ryzen, but Intel, your IHS is that. So if you have a water block that's this, it's great. But if you have a CPU that's flat and a water block that's this, not great. So because of that, you know, but like at the same time, I'm not aware of any like water blocks that advertise themselves as being ridiculously flat. So because of that, I'd probably, like, whatever water block you end up buying, you probably might have to lap it flat yourself. So for that reason, I'd probably go for something with nickel plating, just so that you can see when you've gotten through the copper. Because if you sand off all the nickel on a flat surface, well, you know it's flat now, isn't it? Now, I guess you could also use like a slightly higher grit first, because if the block has like a mirror finish and then you use a higher grit, then you'll scratch it up, and then you can see how long, like, see if you can get all of the scratches off with a finer grit. And if the scratches are all gone, well, it's flat again, assuming that the surface you're using is flat. But anyway, who cares? Like, or, you know, you can just find something that's a very flat edge, and use that to check by just holding it against the block and seeing if you can see any light through it or anything like that. But, or you can just test thermal, you know, you could also just mount it and see how the thermal paste spreads out. But anyway, so yeah, I'm not very pleased with doing this testing with the AIO. Like, I'm happy with the results because that's a significant improvement, but at the same time, like, not okay. Like, not okay at all. So yeah, like, ideally flatter block, flatter IHS, just flat everything, and then use the thinnest part. Like, that's the cool thing about liquid metal is you can use such a thin layer of it, which further boosts the thermal transfer, right? The thinner your thermal interface material, the better. Now then, let's all of my complaints for liquid metal. One, it takes off the inscriptions on CPUs. So that's one of the first concerns with liquid metal is if you run liquid metal on a CPU for long enough and then you take it off, and let's say you killed the CPU or the CPU randomly up and died and you need to send it in for RMA. Well, they're going to have a hell of a time at the RMA center trying to figure out what you sent them, because if you ran the CPU on liquid metal for like a year, 2, maybe 3, there's a pretty good chance you're not going to see, like, nobody's going to see the letters are going to be gone. So that's one of the problems with liquid metal. And I have experience with that one. I dailied a 3960X on liquid metal at one point. You couldn't tell it's a 3960X after I was done with it, like after I eventually went back to thermal paste. So that's one of the issues with liquid metal, is just like, yeah, it ruins CPU inscriptions. Two, it diffuses into copper heat sinks, which it's not the entire alloy diffuses into copper heat sinks. I do believe it's just the gallium in liquid metal alloys that diffuses into copper heat sinks. But the problem with this is basically if you put liquid metal on copper, it does actually kind of dry, similar to how if you have, say, if you have I don't know, say wet sand, and then you put and you squeeze. Well, no, that's not gonna work. Basically, the problem is, think of a fluid with solids floating in it, and then remove the fluid. Now you just have solids. Well, that's what happens with the liquid metal alloy if it sits on top of copper. So the gallium diffuses into the copper, which stains the copper. This is not a problem. It doesn't harm performance in any significant way. And after enough time, it'll stop diffusing into the copper. So once all of your once the base of once the base of whatever cooler you're using is stained with the liquid metal everywhere, it'll stop diffusing into it. So it's no longer going to be an issue. But when it first starts diffusing into it, the problem is it leaves behind the non-gallium parts of the alloy, and that basically turns the liquid metal into a steadily more solid substance, which means sometimes when removing removing a cooler that you have liquid metal between the CPU and the cooler, and there's copper, and it's like a bare copper contact plate. Removing it's going to kind of suck, because you the CPU's kind of the liquid metal basically solidifies into place as it diffuses. The other thing is, as it solidifies, it actually does lose thermal performance a bit. So you might find that if you're doing a fresh install of liquid metal, after a couple months, maybe a year, you'll have to reapply it because it just diffused so much into the copper plate, the copper contact plate, that you need to reapply it because it's no longer liquid and it's not doing its job properly anymore. So that's kind of so it's kind of a hassle to run because of that. It takes off the lettering on CPUs, and if you're using copper surfaces, then it'll diffuse into them, and that can cause some minor. They're not huge issues, but it can cause some annoyances. The other issue with liquid metal is the cleanup. If you're cleaning up liquid metal, it turns into, if you clean it with alcohol, it turns into a dark conductive dust. Conductive dust on electronics translates into major issues. It is the main reason why I don't recommend running liquid metal on, say, GPUs. On CPUs, I don't see too much of a problem with it, because if you ever need to clean the liquid metal off of a CPU, you can literally just take the entire CPU out of the motherboard, clean the CPU, away from the motherboard and away from all of the other components, so that you don't get any of the liquid metal dust all over your stuff. On the flip side, I had an R9 290 that I tried to run, I dailied on liquid metal, and eventually decided, you know what, I'm not going to bother with this. I spent multiple hours cleaning and re-cleaning that card because some liquid metal residue from the cleaning, the initial cleaning, got under some BGA, like a memory chip or maybe the core, and it was artifacting. So I ended up having to clean that card over and over and over and over again until it finally stopped artifacting. So because of that, the cleanup with liquid metal also sucks. So that's kind of the main complaints I have with it, is just it takes lettering off of CPUs, it diffuses into copper, so you might have to reapply it, which is not a big deal because you don't need to, I have one tube of liquid metal and it's so old that I don't know how old it is. That's how little you need. Whereas thermal paste, on the other hand, I go through it pretty quickly. Admittedly, I also don't use liquid metal that frequently because of my complaint about the cleaning thing. But yeah, so on CPUs, the cleaning concerns are not as big, but there is obviously, you still, you want to, I wouldn't use it on GPUs because the dust that it creates is just a nightmare to deal with. And then, of course, it's a spill hazard. If you apply too much liquid metal in your first go, which, again, as I mentioned, I had to reapply I kept adding liquid metal until I got good thermal performance. I would strongly recommend that if you're applying liquid metal to anything, you start with too little, rather than too much. Because if you apply too much liquid metal, it'll spill. And as I said, unlike water, it doesn't dry. It's extremely conductive. Like water compared to liquid metal is an insulator. Liquid metal is like blow your stuff up if it's on the wrong thing. So liquid metal doesn't dry, is extremely conductive, and it eats solder. Because actually, like for, I think conductanol, actually, part of the alloy is actually tin. Which you might be like, why on earth is tin in conductanol? It's for I think it's to make it more adhesive to nickel and copper or something like that, where depending on how you form the alloy, you can get better adhesion properties to various materials. But anyway, so conductanol is not just Gallistan. It's like there's more metals in it than that, to try tweak the behavior of it. But anyway, so yeah, like you applied too much liquid metal, you are potentially going to kill whatever you applied it to permanently. Whereas, so it's better to apply way too little and then have to reapply it, because if you apply too little, you're going to see that, you're going to end up in that scenario I was in where, you have liquid metal, because I applied to both surfaces. So I had liquid metal on the water block not making contact, and on the CPU also not making contact. So I was able to just go like, okay, but there's still enough thermal transfer through this area in the center that it can boot, and we can check the temperatures, and we can see the temperatures are bad. So we can then go and apply a little bit more liquid metal and check the thermal performance again and be like, okay, the temperatures are still bad. Apply a little bit more liquid metal, because the other issue is if you apply too much liquid metal, then it goes everywhere else, and then stuff starts dying. So apply too little, and then just add a bit more and bit more until the performance is where it should be. If you don't know where the performance is where it should be, probably just stick to less rather than more. Because unlike thermal paste, like most modern thermal pastes are non-conductive. So if you spill them on stuff, it's going to make a mess, but it's not going to kill anything. Unless you get it in like your CPU socket, and then it's going to screw up your contact with the pins or something. But generally speaking, if you spill thermal paste, it's not going to kill things. If you spill liquid metal, it's very capable of killing things. So that's kind of the main reasons why I don't use it very frequently, and why you don't see me using it everywhere. Is just like when it on low wattage, on low power consumption things. Again, going back to this, on low power consumption things, liquid metal just doesn't make that much of a difference. On GPUs, it's a cleanup nightmare. On basically in a lot of applications, liquid metal is just like more trouble than it's worth. But when you have a CPU that runs a ton, pulls a bunch of power, and the thermal transfer surface area is not very big, liquid metal is a great option, which in theory would make it a great option for GPUs, but the cleanup sucks. Admittedly, that's more of a concern for me than for most people, because I regularly swap heat sinks and that kind of thing I regularly disassemble things and reassemble them. And because of that, and also with a lot of my CPUs, I have motherboards where it's I run one CPU, then another CPU, then another CPU, then another and it's just so every time if I have to reapply the liquid metal and then clean off the liquid metal, and it's not fun to deal with. But if you're doing a one install, and once it's done right, you just leave it, liquid metal can be really is a great option, I think, for that kind of application. But yeah, for constant disassembly and retesting, it's a nightmare, and that's why I don't use it. But in some cases, yeah, it can get you some very impressive thermal performance. Also, based on the fact that at 244 watts, a 3950X sees such a massive, an 8-degree temperature drop, I'd say putting liquid metal on top of the IHS of a 9900K is probably not that bad an idea, just because a 9900K is also very capable of pulling around 244 watts if you like to test it the way I test it. And so, and I do believe the contact patch of a IHS for a 9900K is even smaller than for a 3950X. So if, you have a CPU that has even less surface area for thermal transfer pushing just as much power, the impact from the liquid metal should be bigger than on a larger CPU that's putting out the same amount of heat. So, yeah. Anyway, Oh boy, I've made this. I've still made this video 40 minutes. Oh man, I have issues. Anyway, that is it. That's finally it for the video. Liquid metal does actually make. Wait, I moved that layer. Oh damn, I did move that layer. There. Yeah. So liquid metal on a 3950X, not a terrible idea. You know, not a terrible idea. Is this the best idea ever? Not really. Like again, like there's a lot of issues with liquid metal in my opinion for recommending it to people, right? It's just like if you have a low wattage CPU, doesn't make a difference. It takes off lettering. It like ruins contact, like it makes copper contact plates very ugly. It can be a nightmare to clean up. It's generally not, it's very dangerous to, like, if you make a mistake with it, like, it's possibly, like, like, it's gone, right? You spill it on a resistor or something, like, bye-bye resistor. I hope that wasn't just a bridge resistor, because if that thing had a value of more than 0 ohms and you just dumped liquid metal on it, well, now it's 0 ohms. So yeah, that's the thing with it. So, but still, on a 3950X, it actually gives a pretty decent thermal improvement. And yeah, in my testing at least, which wasn't super scientific, but like it's good enough to go like, hey, this might actually be worth it. And if you have a 3950X and you're just interested in getting the absolute maximum out of it, you were probably already considering running liquid metal on it anyway. So why am I telling you this? But yeah, like liquid metal is not something you only apply on IHS, or like under an IHS. You can also put it on top of the IHS and it'll work well, assuming that the IHS is small enough and the part that you're putting it on hot enough, which the 3950X very much is, depending on what workload. Like, admittedly, like this is very low voltage, which is like if we ran Prime 95 at 1.3 volts, it would probably pull. Like we could calculate how much it would pull, but I'm not gonna like. End of video. Thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon where you can support me. It enables me to do things like buy a 3950X so that then I can put, test liquid metal on it. What else was there? Right, Patreon. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, the usual YouTube merch. There's a link to that down in the description below as well. And yeah, both of those help out immensely with running the channel. So I'd be very grateful if you check them out. So that's it for the video. Thanks for watching and goodbye.